Let's do the layout of NAND gate. We all know the NAND gate circuit is very simple. We have two PMOSes and two NMOSes. This is ground. This is one input terminal. This is VDD. If this input terminal is A, this is B. Similarly, this is B or A. This is very simple circuit, and we will do the layout of this NAND gate in this tutorial. This is the schematic. In the layout, generally we see the layout of the MOSFET. We generally see like this. This is the gate. In the layout, you can see the contact like this. So this is the gate. This is a drain or source. This is source or drain. So to do the layout in Cadence, before doing the layout in Cadence, I will just draw the layout in this paper so that it will be easy for us to understand. So this layout, this circuit, we can redraw as easy to understand in layout, because when we do the layout, we can see the MOSFET in this form. This is like this. This is drain or source. This is the gate. So if we draw the schematic in this fashion, it will be easy to do the layout. So we will proceed for that. Now I am redrawing the schematic so that to understand the layout it is easy. I am not drawing the layout. I am drawing the schematic itself, but in a different way. So here we have the VDD. Here we have the ground, and I am drawing PMOS in horizontal. Here we draw the PMOS and NMOS in vertical way. Here I am drawing it horizontally. So we have one PMOS over there. We have another PMOS over here. So now I am connecting. Assume this is this PMOS. This PMOS is this PMOS. So we have the gate terminal A. This is gate terminal B. So I am considering this is the drain. So drain is connected to the VDD. Here I am considering this is the drain. So drain is connected to VDD, and the sources are connected together to form the output terminal. This is connected, and this will form the out terminal. Now we have two NMOSes also. I am drawing the NMOSes. This is one NMOS. Here is another NMOS. So this PMOS has terminal A here. This NMOS has terminal A here. So they are connected. So I am connecting them directly. So this B and this B also we can connect. So I am connecting them also directly. Now the remaining connection, the ground connection, which are the MOSFET which is having gate A, the source is connected to ground. So I am connecting the source to ground. So this is the ground terminal. And the drain is connected to the source of the next one. So this drain is connected to the source of the B MOSFET. And the B MOSFET drain, this is connected to the out terminal. So this is the out terminal, and they are connected together to form the out. So this is the same schematic what we draw here in a different way, so that it is easy for us to understand how layout looks like. Now we can draw the layout in this paper. After that we will go to Cadence and do a real simulation with Cadence layout editor. Now I am starting to do the layout. I am doing directly from this schematic, so it is easy for us to understand. So first of all, I am drawing to supply rails. This is the VDD supply rail, and this is the ground supply rail. So I am naming it as ground. It has VDD. So we have our first PMOS. That PMOS A. This I am drawing. We have it like this. Let's make it colorful. So this is the gate, and if you see the layout, you can see things like this is the contacts for source or drain, and we have another PMOS over here. This is the gate of that PMOS. Similarly, we have two NMOSs also, and drawing the gate first. These are the contacts. I am just replicating this schematic over here. We had 4 MOSFETs here. Here also we have 4 MOSFETs. Now, for the time being, I am assuming the blue color is the gate. That means blue color is polysilicon, and this pink color or red color I am assuming as metal 1. So this is the first MOSFET, and this is the NMOS, and this is the PMOS. Their gates are connected. So I am just replicating this schematic to this layout. So they are connected, and we can name it as this is the A. A means this is the input A. Similarly, B also, gates of B also connected. So this is named as terminal B. So these connections are done with polysilicon. Now these two connections are over. Now we have to connect the drain of this MOSFET to the VDD. For that I am using metal 1. So the drain is connected to VDD. Similarly, the drain of this MOSFET is also connected to VDD. Now we have the sources of these two MOSFETs are connected together. That means this is the source of these two MOSFET, and they are connected together with metal 1. And this common point, this connected terminal will be the output terminal. And we have a ground connection for this MOSFET, what we draw here. So this MOSFET is connected to ground. This source is connected to ground. And similarly, we have these two. The drain of this MOSFET is connected to the source of this MOSFET. This is also done through metal 1. And finally, the output of the drain of this MOSFET. The drain of this MOSFET is connected to the common point of these two MOSFETs. So I am taking metal 1 from here and routing like this. We can this is a poly, this is a metal 1. A metal 1 we can route a metal 1 over poly without any problem. So this is the metal 1, and it is connected to this. We don't need this. So the input we have one input A over here, another input B over here, and this is the output. Here we have output, and this is the supply, and this is the ground. Now what is remaining is the substrate connection and the N-well connection for the N-well connection for the PMOS and substrate connection for the NMOS. I am not drawing it here. I will do in the Cadence when we do the layout. Before going to Cadence, I just want to cross check what we did over here. First of all, we had a design schematic or the standard schematic we had. Then we redraw the schematic into this fashion such that we can easily make the layout. And after making this, after we made this schematic, and we are just replicating this in the layout form. So the symbol of the MOSFET is replaced by the layout of the MOSFET, and we made poly to poly connect, gate to gate connection with the poly, and all the other connection with metal. So it will be more clear when we do the layout in Cadence. Let us go to Cadence and do the layout.
Let's start with the two input NAND gate. First of all, make the schematic. So file, new, cell view, schematic. I'm naming it as 2 underscore NAND. Press OK. Press I to add instance. The schematic of the NAND gate is very simple, and I'm using UMC technology, MOSFET, PMOS, symbol, close. This is the width 240 nanometer. This is the minimum width. In the digital design, generally we use PMOS width as double as that of NMOS width. So this 240, I am making it as 480, and I will use 240 nanometer for the NMOS. Since this is a digital circuit, we no need to make this bigger. So one PMOS over here, I'm placing another here. Now we need NMOSes. Now we need ground and VDD. For the convenience, I am using ground and VDD as pins. Not using global pin, I am using just pin input output, VDD and ground. Place it over here, VDD, now ground. Now let's wire the things. The drain of this MOSFET is connected to VDD. Both of the drains are connected to VDD. Their bulk terminal is also connected to VDD. This will be the output terminal, output node. The schematic of the NAND gate is pretty popular, so I'm not explaining what it is and what is the working of it. Everyone knows this. Now we can make the input terminal. I'm using pin. I'm using the name A and B for the two inputs. Oops. This is not input output, it is just input. A and B. Hide. This is A. This is B. For the NMOSes also we have to make the same. Oops. To get a pretty schematic, I am not wiring this A to here and this B to here. I'm just labeling it A and B. So in schematic, if we label two wires the same name, that means they are connected. We need not physically, draw all these wires over here, this B to B, this A to A. But when we do the layout, we have to connect all these, physically. And what is remaining is the output terminal. Press P. It's the output. I'm using out, capital out, as the output terminal. Now let's save this. Saved. And before going to layout, we need to create the symbol. So create cell view, from cell view. Okay, left pin A, B. Okay, ground we prefer it to be in the bottom pin. We can make after also, but later, better to do now itself. Okay, let's delete these things, we don't need them. Create shape line, create shape arc, create shape circle. We are done with this. Press F, save this. I'm not simulating the schematic because this is pretty simple and there is no need to simulate. I'm just doing the layout. Fire, so launch, layout Excel. Okay, to NAND, view is layout. Okay, license issue, and here is the LSW layer selection window, and here is the layout window. So before starting the layout, I want to say that generally for all the standard blocks like NAND gate, inverter, we will fix a particular height for the layout. Otherwise, if you make one layout of inverter a small one, and another NAND gate a big one, and a 3-input NAND gate a bigger one, if you do like this, so the interconnection will be difficult. So what generally do, we fix the height of the layout to certain value. So here in this tutorial I am fixing the size as 8 micro. So for the time being I am using it as 8 micro. Now let's start placing the components. Add NMOSes and PMOSes over here. So browse UMC MOS. First I am adding PMOSes. So we have to select this layout. Before adding, you check it is 480 nano, it's fine. Press F. Now we are seeing just a box over here, PMOS. We want to see what is inside it. So go to options, display, and display level, stop display level, it is 0 now. That's why we are seeing a box, just a box. So you put it as 10. Okay, Now we can see the gate. This is the source or drain. This is the drain or the source. So this is the PMOS. So we have two PMOSes. So just copy, zoom it. I'm placing very near to this. One more options, display. If I want to move it freely, I need diagonal, edit at any angle. Okay, that's fine. uh, let's add the NMOSes. Add instance. Instead of P we need N. This NMOS, so it is 240 nanometer, length 180 nanometer. I'm placing over, for the time being I'm placing it randomly, but two of them together. uh, Now I am connecting the gates together. The gate of this PMOS is connected to gate of this NMOS. Gate of this PMOS is connected to gate of this NMOS. That connection I can, gate is made of polysilicon, so that connection I can make using polysilicon itself. In digital circuit, we generally make connections with polysilicon. It is not a problem. But in analog circuit, we don't prefer polysilicon connections because the resistance of polysilicon is high, so it will introduce noise in the circuit. Since the digital is robust to noise, we can make connection with polysilicon. Keep in mind that in analog circuit we don't prefer polysilicon for the connections. So in the layer selection window, we select the polysilicon, that is PO1. It's already selected. Press R to make a rectangle. We stop there. Zoom that area. Move the NMOS to exactly fit. Press F. Similarly do for the other PMOS also. Press R to start the rectangle with polysilicon and drag it down. If we make so, then they will overlap. For the time being we don't need them to overlap, so what I'm doing, I'm pulling this little bit apart and and there is no problem if they overlap, but for the time being I want to show like this. In this tutorial itself we'll do the other method also. uh, Zoom in, press R. Okay, this is good enough for a connection. So we connected the gates together. For this PMOS gate is now connected to the NMOS gate. Now we need to draw a supply rail of VDD and ground. So I am drawing that first. I am using metal one for that. So in the LSW, select metal one. ME1 is for metal one. So press R to make a rectangle. I am using a big supply rail and copying that for ground also. Zoom it. Press F. Now we have, this is the VDD and this is the ground. Now in the schematic, the drain of both of these MOSFET are connected to the VDD. So this terminal is connected to VDD, this terminal is also connected to VDD, and I am making that connection now. So okay, before making that connection, what I want to make is the body connection. Body is connected to the VDD. So for the PMOS, uh, we need to connect the NVEL to the metal one. So metal one, VDD we are supplying through metal one. So we need the NVEL to connect to the metal one. So we need to create a via that is going from NVEL to metal one to NVEL. So since we have a 2 MOSFET over here, we need a big one. Okay, this is fine. Right. We cannot place it like this because this NVEL is not overlap now. We need overlapping of NVEL so that it is considered to be a single NVEL. So I am placing it like this. So all this part is a single NVEL and the NVEL is connected to the supply VDD using this via. Press F. Similarly, we need to connect the P substrate, that is where the NMOS is there. In P substrate, we need P to be connected to the substrate connection to be to ground. So create via P diffusion to M1. Here also we need bigger ones. Put it very close to, we need more than 4, we put only 4 contacts. So let's make little bit bigger. Instead of 4, put 6. Apply. Okay, and let's move the ground to here. Press F. Before moving, just check for DRC. Is there any error? DRC error is there. Run DRC. Okay, save all. Yes, we have some okay, minimum poly width issue is there. Minimum metal one area. Okay, where is the minimum poly width issue? Okay, here we added a small portion that is not good enough, so we delete that. In the layer selection window we make poly and draw a big rectangle, and I hope that issue will be rectified now. Ashura run drc. Okay, okay. Okay, that issue is resolved. Now the only issue is minimum metal area, that is the source and drain of this MOSFET we didn't connect to anywhere, so that is not a big issue. We are going to deal with that, and now we can make the connections. So first of all, I will make the connection to the PMOS. So the PMOS, this terminal is connected to VDD. Both of the PMOS terminals are connected to VDD. So I am making this connection now. So as we draw in the paper, uh, first of all, in the layer selection window we have to use metal 1, ME1. Now zoom in, press R, escape. So it's already metal 1. There is no issue if we overlap, but for a neatness I am drawing like this. So now this terminal is connected to VDD. So like we draw in the paper, I am connecting this terminal also to VDD. Press R again, start from here, scroll. This is also connected to VDD. Now we need to connect these two together. Press R. Press F. Now the connection with PMOS is almost over. This is connected to VDD. This is also connected to VDD. This terminal will be the output terminal. We have to take it, and before that we have to do the connections of NMOS also. So in NMOS this terminal is connected to ground. Press R. Press F, and these two terminals are connected together. If you have any doubt, you can go back to what we drawn in the paper, and please check that. Press R, and okay, this is the output terminal. Now we have to connect this terminal to this terminal. So what I am doing, press R, press F. Now we need to connect them together. Press R again. Oops. Press R. here. Okay, the connection I made over here is this connection, output terminal connection in the schematic. So now we can say the layout is almost complete, but the gates are still in polysilicon, but generally our pins are in metal one. All the other pins VDD and supply in metal one, output is also metal one, so we need a via from polysilicon from metal one. So create via metal one poly, hide. So we place it one over here and one over here. Before labeling, just check for the DRC once again. Ashura run DRC. Okay, okay, okay. Yes. So we have some issues again. Field poly spacing 0.24. So where is the issue? Oh, this is not connected. So we connect it together. Yes. Then what is the next error? Minimum polygon area. Okay. Oops, this also not connected. Okay. So let's, oh, we have metal one. Just put a small metal one net over here so that they are connected. So run that DRC once again. File, close this one. Ashura and DRC. Okay, okay. So again the minimum metal area, where is it? Okay, we didn't add any connection over there, it is fine. So press R, press F. Similarly for this, skip, so press R. Let's run the DRC again. Okay, okay, okay. Yes, no DRC error found, so we are clear with DRC. Now before going to LVS, layout versus schematic, we have to label this. So label metal one, select, hide, VD, ground, A, B, out. Press escape, run drc. Okay, drc with clear, we have to run lvs. Okay, okay, okay. So it's clear now. Layout and schematic match. Our LVS is also clear. It is saying schematic and layout match. Okay, and see, now we draw these two MOSFET as separate so that the area is little bit high. We can see that what is the width, approximate width we are taking is 5 micro. You can say approximately what this is what we are taking. So we can, if we want, we can make it more compact. Okay, I'm deleting all these supply nets. Delete for better. We can go to options, display, and make this top display level to 0. See what happens. So all these blocks are, so it is easy for us to delete. Only the connections will be shown. Whatever inside the box, it will not be shown. I'm not deleting these. Okay, let's delete everything. Oops, deleted the CMOS also. Options, display, put it back to 10. So earlier we had a metal one connection from here to here, but in this case we don't need to put metal connection. We can drag this MOSFET here and make them overlap. Zoom in. Press F. Now also we can say these are the two MOSFETs with the drain and source connected together. So similarly we can do that for our NMOS also. Here also we have the same connection. So drag it. Let's zoom. Let's see. This is also the same circuit. uh, Similarly what we did previous, we can connect the gates with polysilicon plus R for rectangle, or we can copy this and place it exactly where we want. Here this is not moving to according to our wish. So the issue is gravity. Go to options, display, oh sorry, not on display, options, editor, gravity on, let's turn it off. Okay, now try to move this. Yeah, okay, press F. It is the same situation over here. Press R. Press F. Now the gate connections are over. Now we can draw the supply rail now. Supply rail we draw with metal one. Select metal one. Press R. Press F. We copy for that ground also. Zoom. Press F. Now let's make the connections to VDD. This is exactly the same what we did earlier. Press F. This node is also connected to VDD. Press F. Now this is the common point and this is the output terminal. So before defining the output terminal, I want to make the gate, so I'm just copying this. Deleting the rest of the things. Press F. And let's label. Okay, now AI is already there, so Oh, we didn't make the output connection. Output connection we can make. We can draw this. Press R. Escape. Press F. Press F. Now we need to make this connection, so draw the rectangle, scroll up. Okay, oh, it's became a big one. We don't need that much big one. Let's delete this. Press F. Press R again. And okay, the ground connection is still pending. Press R. Let's label now. Okay, before label, check for DRC. Ashura run DRC. Okay, okay. So we have some issues over here. It is with the PMOS. It is saying minimum P diffusion to nearest 10 plus pickup spacing is 20 micro. Okay, that issue is we didn't add the connection from supply to NVEL. That is that issue, that error. Oh, we forget that. So create via M1 to NVEL. We don't need a big one now. This is fine. Okay, press F. Now we made a wrong alignment here. Okay, press F. Ashura and DRC. Okay, okay. Okay, one of the DRC error what is showing is this minimum maximum and minimum contact size is 0.24 into 0.24, so our alignment is not so proper. That's why the contact is little bit higher than that. So I will just delete this and make this contact proper. Press F and to drag this poly also. Press F. I'm not expecting any issue over here, so press R. Check DRC again, and DRC okay. Yes. Now there is minimum metal area. Okay, error is this one. Error this with this NMOS. We didn't connect anything to that, so that's why it is showing an error over here. We can overcome this in two ways. First of all, one method to do is to make a connection over here, just to make this metal little bit wider. I can just press this R and so we are just cheating that design rule. We are not making any connection, we are just making that point little bit wider so that design rule is satisfied. That is one method to do that. Okay, so no DRC error found. So this is one method of doing that. Another thing, here we don't really need a metal connection, so we can really delete that metal connection. For that, the layer selection window, for that I am deleting the metal one that we just added. And the thing what we can do, the error what we are getting is this metal is not having the minimal size to pass the DRC. But really speaking, we don't need a metal over here, because our connection is through diffusion. So this metal is only needed if we are taking a connection from here. So we can delete this metal and this contact. For that, we can select this both MOSFETs, then go to edit, hierarchy, and flatten. So we are flattening the cells. Okay, now we flattened the cells. Oh, it didn't happen. So select once again, edit, hierarchy, flatten, flatten P cells. Okay, now we can delete the individual elements. I am deleting the two contacts, and this metal wire also I deleted. So now check the DRC. Okay, so there is no DRC. We get rid of that error. So one advantage if we do like this is that we can make the routing through this way also. Instead of doing this way, we can make the routing this way also, but I'm not doing this now. If you want, you can do that also. In certain kind of schema layout, it make the things compact if you make the routing through this way. Okay, I'm just labeling the things. uh, we have VDD, ground, yeah, already we did, B, and out. So you can see our initially it took around 5 micro width. Now we reduced the size to around half of that, not exactly half, but we saved a considerable amount of area. And let's do the LVS, run LVS. Okay, so LVS is fine. That means our layout and schematic match, showing layout and schematic match. I'm stopping here. I'm not doing the QRC or extraction. I'm not doing. We already did that for the CMOS inverter layout. So whoever want to know about extraction, they can follow that tutorial. I'm stopping it now. Thanks for watching.